continue, and it should be recording now.
Okay, wonderful. Hello, everyone. Welcome. Thank you so much for joining our second EMI seminar. I'm Panya Newell. I'm an assistant professor of mechanical engineering at the University of Utah. I'm the chair of the EMI Poromechanics Technical Committee that's basically hosting this seminar series. And today, along with my colleague, Professor Gomi, we'll be chairing this seminar. Today, we have two amazing speakers, Professor Francois Renard and Professor Ange Akono, who will be sharing their recent work with us. But before I introduce the first speaker, I would like to turn the virtual floor over to Professor Gomi to introduce himself and walk us through the logistics of this event.
Good morning, everyone, or good morning, good afternoon, and good evening, everyone, because I know that people are from different time zones. Welcome to the second EMI virtual seminar series. Today we are going to have two talks, as Pania mentioned. Each talk will be 30 minutes. And then after each talk, we are going to have about 10 to 15 minutes of questions and answers, and basically delve a little bit more to make sure that we learn and understand and appreciate the concepts presented in more detail. So without further ado, I give back the podium to Pania to introduce the first speaker, and with that I conclude. Thank you.
Thank you. So our first speaker is Professor Renard, who is a professor of geosciences at the University of Oslo, Norway. He's the director of NORAD Center, a cross-disciplinary physics geoscience center at the University of Oslo. His research interests are fault dynamics, earthquake nucleations and propagations, and fluid flow in the crust, which with the emphasis on geohazard mitigations and sustainable explorations of georesources. Today, he will be talking about imaging flow and deformations in rocks using large international facilities. With that, I guess I'll pass the virtual floor to Professor Renard.
Thank you, Panya, for this very nice introduction. So I will just dive in the topic from the beginning, if I can. So what I will discuss today is what I consider to be a real strong innovation in experimental poromechanics in the past 20 years, is the fact that now it's possible to see inside a sample, a rock sample, in the lab or in a big facility, as I will show you, while processes occur. So these processes, it could be chemical reaction, fluid flow, or deformation. And this is possible because many of these facilities have been built like this in Grenoble, where there is this ring, which is, let me check, put a pointer. You see the pointer now?
Yes.
Yeah. So this ring, which is a big X-ray source, it's called a cyclotron, and this one, which is a nuclear reactor, which produces neutrons. These facilities exist all over the world. There are many in Europe, in Switzerland also. There is a cyclotron and a neutron source. One is going to be built in Sweden, in Lund. It's called the European Spallation Source. There is the one in Grenoble and the nuclear reactor here. And in the US, there are also the same kind of facilities in various places. These two kind of facilities, they use either the X-rays. So the X-rays, that's electromagnetic radiation beyond visible light. So in the range of angstrom to nanometer wavelengths. And they use also neutron, so that's a neutron source. The neutron is this part of the core of an atom that does not contain any charge. And so one of the reasons neutrons are quite powerful is that they can propagate through matter without interacting with the atoms. So this is this image made by the Paul Scherrer Institute in Switzerland of the same object. It's here, it's a camera. Image with the two techniques, neutrons and the X-rays. Neutrons are very sensitive to hydrogen mainly, so the plastic part of the camera, and to few other elements like cadmium. I will come back to that. And the X-rays are mainly sensitive to the atomic mass of elements. So the same object image with two techniques, for example, if you want to figure out if the camera contains a film, which is this part, neutron will be more useful. If you want to see the metallic part of the camera, like the bolts here, the X-ray will be more useful. So depending on the scientific question one wants to solve or the experiment one wants to do, one or the other technique can be used. These techniques, they allow to progress on a challenge, which is how to image processes in 4 dimensions, so 3 dimensions plus times in geomaterial. And they can allow to image directly fluid flow in rocks, porous medium, or other geomaterials, and also image deformation and other processes. So as you know, a rock or a geomaterial most often is not transparent, and these imaging techniques allow to go inside. So that's the same core here. It's the same experiment. It's a core of a bentime sandstone, around 20% porosity, where on the top, on the right side, the fluid that contains cadmium is injected, and on the left side, there is just water. And what we see is that the cadmium-rich fluid and the water, they circulate downwards in the rock sample, and they will start to mix. And so there is a front of a dispersion that propagates also at the interface between the two. And on the right side is the same sample in which we have injected a solution that precipitates calcite, so clogs part of the porosity. The porosity will go from 22 to 20%. It will change how the two fluids will mix at the interface between the two systems. So this kind of thing can be imaged here with neutron, and as you see, we see the fluid and we almost don't see the rock. I will focus now the rest of my talk on X-ray tomography, so using X-rays. And the main innovation, perhaps in the past 5 to 10 years, is that several groups have developed technique to put geomaterial or rock samples at conditions of pressure and temperature relevant for the given scientific question. So it could be several kilometer depth in my case, and to study in situ the deformation of these samples. So I developed this one with Benoît Cordonnier at ESRF in Grenoble, the European cyclotron. We developed this HADES rig where there is a small rock sample, centimeter scale, and this apparatus can reproduce conditions of pressure or of temperature of 3 to 4 kilometer depth. Another one has been developed by the group in Scotland, in Edinburgh, by Florian Fusseis, Ian Butler, and collaborators. And there is this recent machine just published 6 months ago, developed at Johns Hopkins by the group of Hurley. And in the US, just raise your attention to this network funded by NSF called In Situ Studies of Rock Deformation, where the idea is to federate the scientific communities working with these neutron and cyclotron techniques. So what can we do with these techniques? I show you here 2 examples of rocks we deform in the group in Oslo. On the right side, it's a Carrara marble. So it's a small cylinder of rock that has been deformed until brittle deformation. And what we see is the formation of microfracture and the shear zone. At the end, the sample is broken. The left side is a rock which is called a monzonite. It's like a granite. And this rock contains microfractures that appear in blue here. They are labeled by a technique called segmentation in blue. The rock is at a confining pressure of 25 megapascals, so there is a jacket around the rock that applies a lateral pressure. The rock is shortened in the vertical direction. The stress is increased. It reaches a yield point as a strain versus stress curve. At some stage, the entire macrofracture will form a connecting path to the sample. The rock will collapse, creating the miniature earthquake, the sample. So that will be the last image of the movie. The rock has collapsed. So now it has collapsed. So we can see with this kind of experiments, we can look at how the approach to system size failure in rock occurs at this scale. Another potential application is to monitor chemical reactions. So perhaps many of you have done this experiment. You want cold water, you put a bottle of water in the freezer, you forget it for the night, and when you come back the next day, the water has transformed into ice. This has expanded and broken the container. That's called the phase transition with the volume increase from liquid water to solid ice exerted the force that has broken here the bottle. So this kind of process is called reaction-induced fracturing. It occurs also in nature in many places. You can have salt damage. It also can modify the durability of cement if some salt precipitate. The rock weathering process at the Earth's surface occur with this process is that there is a chemical alteration of the rock, microfracturing, and then the rock evolve into a sand. Corrosive, for those who live in cold areas, the rock metamorphism, so the transformation of some rock of the Earth's crust into other rocks with phase transitions. So here I show you on the right side, it's a movie. I will come back a bit later to the same movie. It's an experiment at in situ condition where we start with a material which is in the middle here, which is located into a rock container. And this material is periclase, it's a magnesium oxide, which can become unstable under the addition of water and evolve into brucite, MgOH2. So that's a movie of this, a piece of periclase, which we add water, evolve into brucite, and this reaction occurs with a solid volume increase of 110%. So a bit like the liquid water to solid water, which occur with a volume increase of a few percent. Here, the volume increase is much bigger. So the initial MgO, which was orange, transformed into brucite, one, MgOH2. I put it transparent, so we can see the fragment of the original material starting to be fragmented and spread around. So the brucite would be between these grains. Experimental conditions, it was below 200 degrees with a confining pressure and a porphyry pressure applied on this sample. The duration of this process is 140 minutes, and each 3D scan made in a cyclotron inside this apparatus I mentioned before each scan takes between 2 and 3 minutes. And we started to study this process because it's analog to a major process in the oceanic crust, which is called serpentinization. It's the transformation of mantellic rock from the mantle into oceanic crustal rocks. We evolved this experiment also where we put this periclase here into a rock container. So there is the periclase, MgO, into a rock container. And the idea that if upon addition of water, it will evolve, this periclase will react, inflate, volume will increase, and will start to break the rock around. So all this sample assembly is installed into the Hades rigs. We have X-rays, and we can do 3D imaging through time of the process. And that's what we get. We get this, so that's just a slice view of the sample through time. The periclase here in the middle will start to react, produce brucite. So brucite appear here in dark orange. And at some stage, this brucite will exert a force and start to break the container. We can see fractures, and that's the shape of the container at the end, where part of the periclase has been transformed, that was in the center part, and the fracture network has formed into the rock container. And that's perhaps the link with the next talk by Ange Thérèse. We'll talk about CO2 reaction in basalt or in oceanic rocks. And one possible process, we don't know yet, but that's a possibility, is that during this chemical reaction in oceanic rocks, some force could be exerted by a transforming material, creating cracks that will be filled, for example, with carbonate minerals. So I move now to a second part of my talk. The first part was to present what can be done with four-dimensional imaging. And the second part, it will be a bit more what to do with the data we get. And what can we say with this data, and where we should be careful when we interpret this data. So on the right side, it's a piece of, it's a sandstone. What is white is a quartz grain, it's a Fontainebleau sandstone. What appears in blue is the porosity. This sandstone is at 20 MPa confining pressure, and the stress is applied from the top, the bottom is fixed. And as the stress is increased, the fault, in fact, you will see two conjugate fault start to develop. We can image it with cyclotron imaging, the development of this network. And that's the data we have. We have rocks or geomaterial that evolve through time. And we are interested, for example, to see how the porosity or the fracture network will evolve with time. And I would like now to concentrate the rest of my talk on these two questions. As you see here, I have selected some zones that are blue, that's the porosity. And do we make mistakes? Or how accurate are we when we extract porosity in this kind of image? The second question, which is relevant for many people in the geomechanics community, is in a sample like that, as we approach failure, system size failure, how does a representative elementary volume, does it exist first, and how does it evolve when approaching failure? So the first question is, now we get the 3D data and we try to extract quantity, for example, the porosity. So here is a cylinder of granite. Porosity is in blue. So every time there is a little blue dot, it means that it corresponds to a little pore. And we want to ask the question, how accurate are we when we extract this porosity? Usually to answer this question is quite challenging because this imaging technique, they have a given spatial resolution. So you can image pore at this spatial resolution and not below. And it's very difficult to know the ground truth value of the porosity of this sample at a given resolution. So imagine that the sample is 2 millimeters, each pixel is 5 micrometers. What is the porosity of the sample at 5 micrometer resolution? So that's what the question I try to answer. So to answer this question, we decided to take two images of the sample, so the entire sample and the zoom. Possible now to do that in many cyclotrons, to zoom inside the sample. So the red image is the porosity at a resolution 10 times bigger than the whole sample. So we can zoom in the sample and extract more pores. And there is one thing you can start to see is that the red image, so the sample image at higher resolution, is different than the blue image, just because at higher resolution we can image thinner fracture that do not show at low resolution image. So we have these two images. Now we can start to compare them. So let's take three different slices. So horizontal slice in the red box. The low resolution, the high resolution. So the color here from blue to yellow is the equivalent of a grayscale color. Some minerals appear. So this bright spot, yellow spot, it's the rock is a granite. So this bright spot is an oxide with high density. At high resolution, perhaps all of you can see there is a fracture, and we can see it also at low resolution. There are some circular patterns here, which are some artifacts of the acquisition in X-ray tomography that can be removed partly, or sometimes they are still there. And there are perhaps also, I don't know if you see it, but around these bright spots, there is also a dark area. So it looks like there is a fracture at the edge of this mineral, but it's not the case. It's an artifact also of the acquisition. It's because here we work in phase contrast, and the phase contrast will be enhanced at the interface between the strong absorbing and the less absorbing mineral. So this image contains artifacts. We have just to be aware of that. And the question now is, if I extract the fracture here and there, which kind of error do we make? That's what we did. We took some of these slices. That's the low resolution. It's the high resolution. And that's the yellow spot is what is identified as a fracture or a pore. So at a higher resolution, we take more, but still the main fracture here, we still detect it in in the low resolution image. So how do we extract these fractures? Is that we take the grayscale image, we make an histogram of this grayscale image, and that's a simplified version or idealized version of the histogram. This histogram will contain two peaks. The peaks will be the rock, that's the main peak. The small peaks here will be this dark area, which correspond to fractures. The way to separate from the two different material, the fracture and the rock, is to look at where is this inflection point. So it could be either a valley, like in this histogram. If the two peaks start to be closer, it will just be a minimum of the second derivative of this histogram. So we identify this valley and we say, okay, all the cells on the left are fractures in porosity. All the pixels on the right are rock, and that's how we select the yellow and blue pixel here. And then we can make histograms of what this algorithm can pick. In the high resolution, it's the continuous line, and low resolution, that's a dashed line image. Change a bit this threshold. So the dashed vertical line is really the minimum, and then we change a bit the threshold by some gray value, red gray values on the left or on the right of this limit. And we can do that, for example, for the volume, the histogram of all the fractures detected here, all the single fractures, make an histogram of this volume of these fractures, make the histogram of the surface area of these fractures, histograms of the length. So what is the length of the fractures and what is the aperture? First, we see that if we change a bit this threshold, the lines of the histogram do not change much. They change a bit, but not much. But there is a big difference between the high resolution image here, the low resolution, the dashed line, where, for example, for the smallest fracture volume, the low resolution find more fractures. The reason is that if a fracture is within one voxel, let's say it's like 3 micrometers, it will be detected at the fracture in a voxel which is 6 micrometers. So a fracture of a volume of 3 micrometers to the cube will be detected as if it was a bigger fracture. That's why this dash curve here, low resolution, are above these ones. And we can do the same exercise for all these properties of the fractures. What we get, so let's concentrate only on the top left figure. So that's the threshold here, the grayscale. So that's the value of this dashed line. That's the high resolution image and the low resolution image. We change a bit the threshold. And we want to calculate the total porosity of this volume of the sample that has been imaged at 2 resolution. The low resolution image finds around 1%. High resolution image finds around 1.3%. So there is a difference. And that depends also, the scientific question you want to ask is, if the scientific question is what is the porosity of the rock, it's 1% plus or minus 0.3%. But if you want really to look at more details, for example, if we look at the surface area, there is a large difference between the high resolution image and the low resolution image. No, the high resolution, sorry, and the low resolution. So depending on the properties, resolution will matter. What we also studied is this image, they come with some noise, not only the resolution and the noise. There are two categories. Either it's like a speckle, so point noise in the system, or the image is blurred. So if we start with an image like that, which would be the true image, we can change the resolution, so zoom more or less. We can study the effect of noise or blurred. To give you any idea, if we start with an image like that, which is just black and white, so the histogram of this image will contain two kinds of values, either very white pixels or very dark pixels. by adding this speckle noise, the histogram will start to evolve more from this bimodal distribution to a flattening of both peaks, and with a limit between the two peaks that will start to be difficult to estimate. We studied this effect of resolution, noise, and blurred on the volume of the fracture or the porosity estimated, surface area, the length of the fracture, and the aperture of the fracture. This vertical axis is the output we get minus the ground truth value, so the original image normalized by the original image. For example, the resolution change the volume of the porosity by 10% if you change the resolution. Noise can change this by up to 100%. Blurring change this value by 500%. So if you start with a rock with 1% porosity, by blurring the image, we'll get 5% porosity. So we have to have here big errors. Probably the biggest error is for the surface area, where between the resolution is an important role. So this image, when we process them, we have effects of resolution, spatial resolution of the acquisition, noise. And when we start to extract quantities like porosity, fracture network, I didn't mention permeability, but permeability, water flowing in this fracture or this fracture will have probably a different permeability. What is interesting, you don't see it on the image, but the porosity of this one is larger than this one. So this one is the low resolution image. Porosity 1.4%, and here 1.1. The main difference, so is not the porosity, that's the surface area. That's very visible that this red image, the surface area of the fracture are much bigger. And the consequence, for example, if we want to study chemical reactions at the interface, at the fluid mineral interface, this surface area will play an important role. I will finish my talk, so the last 4 or 5 minutes, by a question which I think we were asked this question 2 or 3 years ago, which was, does the representative elementary volume exist in your experiments? And the answer was, for us, intuitively, it was to say that we take a rock like that, so that's 3 kinds of rocks, and when we approach failure, the rock will fail. See, fracture spanning the side of the system will develop, and so the representative element will be larger than our sample. So we took 11 experiments, and we studied this representative element volume. So this notion of representative element, I will try to explain it. If we take the entire sample, we look, for example, for a porosity. So if we take the system size, the size of the box, and we get a porosity here, and then we start to divide the sample in smaller boxes, we see how the average porosity, the standard deviation of the porosity evolve, the box size decrease. Usually we get a curve like that, where both the variability and also some quantity will increase will change with smaller volume, and the reason is that for some small volumes we could have a volume only that contain a fracture, and that will have a very high value. So the way we did it, we took our samples, we followed this procedure. So the definition we took from the representative element volume is the smallest volume for which some property of the system does not vary significantly from the property calculated throughout the system. And the property we study here is the porosity. And this is an important concept because it's used, for example, to upscale geomechanical processes. When you do modeling, you want that in one of your element cell of the model, the properties do not depend on the size of this element, for example. So we have 11 of these samples at different evolution, far from failure to close to failure. We calculate as a function of this side of these boxes. We calculate here the porosity and we measure the standard deviation, and we define this. We use this coefficient CV, which is just the standard deviation divided by the mean. So it's called the coefficient of variation. And we can see also, we can measure how this coefficient of variation will depend on the size of the box we use to calculate the property. And we define a representative element volume where both curve here flattens. So it means that when you increase the size of the box, the property does not change. And also the coefficient of variation falls below a limit. We took 0.5 here. So to get a bit an intuitive view of how this coefficient of variation vary with heterogeneity, we also created synthetic images. So that's 2 images of synthetic sample with fractures, either tiny fractures spread everywhere, or tiny plus bigger fracture, so spread more or less everywhere. And we calculate the porosity, so that's the surface area of these black patches, as a function of the size of the box used to count them. And for example, this sample B, which is more heterogeneous and contains bigger heterogeneity, will have REV, representative element volume, bigger than the one on the left. That's because the heterogeneities are larger. So let's apply that to our samples. So we have 11 samples. I show you here 4. I show you 4 samples where the black curve is far from failure. So the sample has developed some microfractures. And when we approach failure, sample contains more microfractures. REV, close and far from failure. For some sample is very close. For some sample, the REV will decrease when approaching failure, which is not very intuitive. I will come back to that. And for some sample, it increases a bit. What we have seen also is that for the 11 experiment, when we go from no stress to failure, failure is 1. Some experiments, we can define a REV over the experiments. That's a yellow box. For one experiment, there is no REV. It means that the sample is so heterogeneous that the property cannot be defined at the site of this sample. For many samples, it's or for a few samples, for sometimes there is no REV, sometimes there is REV, and so on. So the rocks here, samples, so the blue patches, they correspond to rocks for which the fracture in the rocks tend to be very long, thick, and more volumetric. And it means that when the sample hosts a fracture like that, and the fracture starts to be the side of the sample, there is no REV in this sample. But in average, for many samples, we can find the REV and even throughout almost at the end to failure. So how does this REV evolve for the 11 experiments? So a different color here is an experiment. The REV is given here in micrometer. That's the distance to failure. 1 is failure and 0.5 is far from failure. And we define the distance to failure at the stress at which the sample is. So at failure, it's 1. And no stress is 0, and all the intermediate between. For most samples, this REV will either does not change or slightly increase, and for a few samples, it will even decrease. When, for example, there is no graph, it just means that, if you remember, this one does not have a REV, so we cannot define it. But what is interesting is that now, if we take all the REV, we can calculate for the sample which are between 50 and 75 the distance to failure, so far from failure. For the sample which are close to failure, for the 11 experiments, we can calculate REV. There is not a big difference between the REV. So it means that in our samples, what happens? More microfractures are created. So sample is damaging when approaching failure, but they damage in a homogeneous way. So meaning that if you compare the REV of this system and this system, where the fracture are more or less same size, this one that contains more microfractures is still very homogeneous. It's just a sample that is damaged with microfracture everywhere. In this case, for example, if we calculate the coefficient of variation, the function of the volumetrics of the side of the little cube to calculate the property, this one, for example, the REV of this one will be slightly smaller than this one. Just because adding fracture everywhere will make the sample more homogeneous statistically than the sample that is not damaged. And that was not completely intuitive to find this result for us. So, and that's my conclusion. So these large instruments, they have opened a new area in experimental poromechanics and geomechanics, and they will develop even more. The communities are getting bigger. I didn't mention machine learning, but with these big data, they are now deployed. With the risk is that sometimes we will get results and we will need to understand them. And that's why I wanted to point you on these two pitfalls, or to be careful: spatial resolution, noise in the data, existence of a REV. And that's important to be aware of these limitations before interpreting results, even when they will come from machine learning. And perhaps just I give you a tip for some of you who want to do this kind of experiment. It's an obvious tip, but it's something I learned in the past years. It's really worth, when you do this experiment, to spend a lot of time to make your experiment nice with very low noise, relevant spatial resolution, than spending time after to try to find properties into 3D images that contain noise and that don't have the right resolution. To finish, I would like to thank the teamwork that has been done. Every year we go with some colleagues in this place in France to discuss our results. And the people who have contributed to what I have shown you this afternoon, it's the main one is Benoît Cordonnier, who is building all this apparatus and operating the beamline at the cyclotron in Grenoble. And then Chao Jiang, Lima Candula, Irina, who are PhD, Paiman. Jess McBaig, Gautelinda, Marthe Guren, who has postdocs, and Wen Luzu, who is heading the NSF network I mentioned before, and Tanguy Leborn and Joachim Batista. I would like to thank you for your attention.
Unmute myself. Thank you, Francois. We have a few minutes for questions and answers for Francois. You can raise your hand, ask questions, or place your questions in the chat box. And maybe I start first myself. So is the size of RVE depending on the resolution that you perform your scanning? Because I imagine that if you basically start at a smaller scales, you will be able to see some sort of a separations of scales. You find different characteristic lengths of scale for different problems, right?
So I think it will depend a bit on the property. It's on the REV or which property. On the porosity, what I showed you is that the porosity, at least for the sample I have studied, doesn't change much with resolution. So the REV will not change much. But permeability could change a lot, because the smallest resolution will see more and more fractures, and particularly if the low resolution does not connect the fractures. If they are not connected at low resolution, the high resolution will change a lot the permeability. So REV will change with resolution, definitely. Will that change a lot? It will depend on the property you want to study. The main one will be, the two main ones that I think for me I would be careful is the surface area. This one could change a lot, and the surface area between of the fracture and the permeability.
And maybe on a follow-up question, I'm really curious. You can also study the pore connectivity, right? Yeah, because I mean, like, the permeability is not only the surface area, but also how the pores are connected to each other, right? So you could analyze using these scans, these pore connectivities as well at different resolutions.
Yeah. So connectivity will change also probably. We didn't do connectivity on this system yet, but that's.
But the high resolution
nice.
data is available.
Yeah.
Excellent. Pania, you had a question.
Yeah, thank you so much for the wonderful talk. I have actually a bunch of questions, but along the line of the RVE, since we were talking about that. So the RVE size, basically, it depends on the properties that we are interested in. Is that correct? So it means that every time that we are interested in the different properties, we need to have different size RVEs. And how do these come together when we are looking at the entire system? So we want to have the simulations that we are interested in mechanics, we are interested in permeabilities, and then chemistry. What would be, we pick the largest RVE among all of them, or how does that work?
So I think it depends on a bit on the discipline. In geoscience, we have heterogeneities at all scales. You have the grains, then you have the sedimentary layers, there are fractures, and you go to the continent. So how to define a RVE? Here, it's perhaps not even relevant because we need to put to account for many of these heterogeneities. So we have to identify all this length scale that will control the process we want. If we want to study an earthquake, for example, that propagate over 500 kilometer long and 20 kilometer depth, it will meet many of these heterogeneities. So which one are relevant? It's not clear yet for me. So that's one way. So it's to say that RV, we have to be careful you cannot apply it to everything. It's the way I see it. It's used a lot in reservoir engineering, in civil engineering, because when you make a building in concrete, you want that what you test on a small sample, the entire building will react the same. So that's where this notion is important. But to simulate a building, you will have to have all the interface or the shape of the building, from the size of a small element to this entire size. Yeah.
Thank you. So that I guess that brings me to the next question, that since you addressed point out the scale concept here, how does all these synchrotron studies and these smaller scale studies, they translate to the larger scale? Because we want to understand this for the I don't know, to maximize the potentials of the energy or storage in the subsurface. How can, or other applications of the I guess geosystems, how does these smaller scales that translate to those larger?
So that's that's a fundamental question, which is not related only to synchrotron. It's just to how to relate measurement at small scale done in civil engineering, geomechanics in the past 100 years to large scales. So which kind of properties can we extrapolate safely from the small to the large scale, and which one where it will be more difficult without knowing all the heterogeneities until the scale of the system you want to simulate. So for example, there is there are upscaling method. Another one also that I have used, at least for the sample I have studied, is this concept that, for example, fracture or system size failure is a critical phenomenon. So there are microfractures that form in the system that will start to form to accelerate their growth toward failure. And that failure, there is a divergence. And this divergence depends on the system size. So if we are able to understand how all these microfractures grow, connect, and will connect at the size of the system for a small sample, we can use this concept of scaling. So scaling growth from a small scale to the large scale.
Excellent.
Thank you.
The question from Angie.
Okay, thank you for an excellent talk. I had a question, Francois, regarding the anisotropy, because the system that you showed were fairly isotropic, but if you were to have something that's anisotropic, how would that change, let's say, your RAV or even the way you are processing your data?
So we, yeah, that's, I didn't, what can I answer to that? That's a good question. So let's start with what I know. We deform shells. So shell, they have laminations, and we deform sample where the laminations are parallel to the axis of the cylinder or perpendicular. And then just this, the process is very different. Just the deformation mechanism. When you compress shell where the layers are vertical, what happens is that you start to open between the layers. So it's like if you want to deform a book, either you open it and then it opens along the pages. But if you want to compress it perpendicular to the page, it will deform very differently. So heterogeneity will control the deformation. Anisotropy probably could make that REV is anisotropic as well. You will have an REV which will have a property of a tensor. Why not? Can we imagine that? I'm sure that people have tried to imagine that. But that could be something like that, yeah. And that's particularly important for permeability, because this one can be strongly anisotropic.
Okay.
And by the way, if it is anisotropic, it means that we should probably take the largest value of the REV to be safe.
Makes sense. Thank you, Francois, for the excellent presentation. In the interest of time, we are gonna move to the next presentation by our good colleague, Professor Ange Akono. I'm gonna give a brief introduction. Angie did her undergrad studies back in France. I think that it was in École Polytechnique. And I think that she also did a master's degree, and then she came to MIT. She did a master's and PhD. We overlapped for a few years. We started together. I was about to start my PhD work. They said that Angie is going for defense. So she's extremely sharp and talented. And I mean, one of the major contributions that Angie did, she started to look at the scratch test, and through the scratch test, she derived some analytical formula and some in-depth studies whether she can derive some information about fracture properties using this experiment. And this was one of her major contributions. After graduating from MIT, she went for a short stay at UIUC, and then now she's at Northwestern, where she works on mechanical properties of materials across scales in very different applications, from biological system to geomaterial to concrete materials, and even materials for extraterrestrial applications, for example, for Mars. So without further ado, we leave the podium to my good friend, Angie. Thank you.
Thank you, MJ, for the kind introduction. It's really a pleasure to be here and presenting my work. Let me go ahead. I'm not able to share screen, sorry. Can I share my screen, please?
In the US, it costs you something. But let me look. I have to be able to give you access now.
Okay.
I think that you should be able to do it now.
Let me one. Yeah, now I can do it. Okay, good. Okay, so what I'm going to be presenting, and I really like just coming back from what Francois presented, I'm really going to focus here on CO2 geological sequestration and just understanding, because Francois was working on kind of this coupling between chemistry and microstructure and properties, and this is really where I'm going to be building on, and just trying to understand within the case of CO2 geological sequestration, what are the chemical changes that occur and how are they coupled to microstructural changes, and how are they also coupled to a mechanical property change? And that's something that's going to be really spanning several length scale from the nanometer all the way to the millimeter level. in this case. So this is the outline. I'm going to talk about the engineering motivation. Here we use kind of the Illinois Basin Decatur project as an example, and that was actually a project that was commissioned by the U.S. Department of Energy. So I'm going to be presenting that project. And I'm going to highlight what are the research questions and the hypothesis that I'm doing. Then I'm going to present my nanoscale mechanical problem, my theory behind it, and what are the major findings that we had in this case. So the motivation is really the U.S. plans, or the current administration has a plan to be a net zero economy by 2050. That means that we would be producing no net CO2 emissions. And one of the ways they want to be able to do it is to decarbonize the energy sector by 2035. So decarbonizing, there are different routes. One of them is emphasizing clean and renewable energy. Another one is emphasizing low carbon energy, like nuclear energy. And then another way is just kind of looking at CO2 underground, geological storage of CO2 in this case. And this is the one we're going to be focusing on for the talk of today, that is CO2 geological storage. Okay, so when you think about geological sequestration of CO2, so in this case, we had actually in terms of the way it works, CO2 is being injected, supercritical CO2, and it's really going to go at a certain depth. So you can see like the depth can be in the range of 2,000 meters underground in this case. And it's just going to, the idea is to be able to store it within a saline aquifer. It's going to be stored within the nanopores and the micropore in this case. So there's a project that was commissioned by the U.S. Department of Energy, and it went from 2014 to 2016, where they were injecting liquid CO2 within the Illinois Basin. And you're really seeing here the location so that you have an idea of where they conducted that they started pumping and injecting CO2. And what happened is you had 1 million megaton of CO2 that was injected over 3 years. Something that was really interesting is they put geophone on the surface to be able to monitor the seismic emissions that will occur. And this is what this chart is showing, is really the magnitude. So you have kind of just like low level versus high level in this case. And we were looking at what we call induced seismicity, where you kind of have like something that is small, but not that negligible in this case. And what they noticed is that when there is the injection led to a surge in seismic emission, there are more than 6,000 microseismic. Again, we're looking at microseismic in this case, events that were recorded during the period, during the 3 years when they were injecting CO2 underground. And what you're seeing there is a chart showing you the different microseismic events. So you have in this case 2014 when they started. Then you have an increase in the 2011 when they started, sorry. Then you have an increase in the microseismicity. And what was interesting is 2014, they shut down. They stopped injecting CO2 and they would think, okay, well, microseismicity should stop. Actually, it didn't. They will still record more microseismic events even after they had stopped injecting CO2. In this case. So this observation of microseismicity is kind of hinting to several mechanisms that might happen, but overall there's kind of this feeling that there might be some type of mechanical weakening that is occurring within the host rock as a result of rock fluid interaction between the host rock and, in this case, the brine saturated with supercritical CO2. So this is kind of what we wanted to be able to explore. Moving on to the research question. So we wanted to understand what is the impact of geochemical reactions on the mechanical properties, but also on the physical properties. So the host rock in this case was the Mount Simon sandstone. So in terms of, so we went to the scientific literature. Typically what has been recorded is that when you have a host rock that is going to be in prolonged contact with supercritical CO2 mixed with a brine, there might be some mineral dissolution, there might be an increase in permeability, there might be an increase in porosity, there might be the formation of channels, and there might be also secondary mineral precipitation. But again, we wanted to see what mechanisms are applicable to the case we are looking at, in this case, the Mount Simon sandstone, what type of geochemical reactions are prevalent, and how do they lead to changes in the microstructure and changes in the mechanical properties. So our research hypothesis is that the dominant mechanism is going to be mineral dissolution that will occur. And that will be because of interaction between the liquid CO2 that is going to dissolve into pore water and acidify it. And as a result, there's going to be a reduction of mineral strength along grain boundary. And this is going to be promoting fracturing at a lower stress in this case. And it was really interesting to kind of notice that we have a multi-scale problem. So you have several time scales. So I told you the project was run over time scale of 3 years, but I'm going to present later experimental or lab experiment that I run in the land scale of weeks, and then also experiment that I conducted, mechanical testing that I run in the land scale of hours. So you really have several time scales, but you also have several land scales. So if you look at the host rock, the Mount Simon sandstone, if you look at the level of 100 micrometer, you have really something that is both porous and granular. So you have the different grains shown here. This is the scanning electron microscopy images. And you have different mineralogy. So you can see you have like light gray and dark gray phases. You have like quartz and feldspar, and you have pores that are going to be in black. Then if you kind of zoom in at the level of tens of microns, you see that actually it's a little bit more complex. You have micropore, you have quartz and feldspar, and surrounding the grains, you have the clay. So the clay are going to be acting as cement that are gluing the grains together. And then if you go to the level of micron and below, then you're going to have the clays that are nanoporous themselves. So you have, again, more scanning electron microscopy images, but also electron dispersive spectroscopy. And it is used to be able to really understand, what are the physics, because you have a system that is heterogeneous, that is granular. So you have the different mineralogy, feldspar, quartz, and clay in between the grains. You have different morphology of the grains in this case. But also when you look also at the characteristic length or size, you have the clay, for instance, that's going to be also nanoporous. So you have two types of pores. You have micropores between the grain, but you have nanopores within the clay that is surrounding the grains in this case. So this kind of led us to try to think, how do we approach the behavior conceptually, and what are the different landscapes that are going to dictate the behavior, and what are the different type of changes that occur when you're going to have then this interaction between the rock and the CO2 saturated brine. This is another SEM images showing again the rock, which is, again, we've seen it granular. You have different mineralogies, and that is represented by the different, the dark gray and light gray phases. And you can see here you have the clay surrounding the grain again. So we had this idea of granular, heterogeneous, and dual porosity. And we have more pictures again showing the clay. It's really fascinating because the clay plays such an important role. It is literally the glue holding the grain together. So what happens if there's some types of damage that's occurring, but what would be that kind of damage? And you can see the different sheets because you have something that is really, really nanoporous in this case. Okay, so in terms of objective, we wanted to be able to apply depth sensing methods to be able to observe and monitor nonlinear behavior, morphological changes, and chemical reaction processes in Mount Simon sandstone rock following exposure to CO2 saturated brine. We wanted to be able to quantify alteration in mineralogy, in surface roughness, surface chemistry, wettability, pore space geometry, and porosity. We wanted to be able to measure the failure criterion at different scales, but ultimately evaluate changes in geomechanical properties as a result of aging in CO2 saturated brine. Okay. So let's kind of talk a little bit of the methodology that we use. So I talked about the field project that was conducted, but our work was actually looking more like at lab experiments. So we had incubation experiment on Mount Simon sandstone. And this is the apparatus that we use, my colleague used. So I had collaboration with UT Austin, University of Texas, Austin, and also collaboration at the University of Southern California. And essentially what you can see, the idea is to be able to create a microreactor. And within that reactor, what you're going to have your sample here. And the sample is going to be in close contact with synthetic brine in this case, and supercritical CO2 under high temperature and high pressure. That is the basic idea in this case. Now, what are the ranges so that you have an idea when I talk about high pressure, when I talk about high temperature, what are the numbers? What are the range? So you have, for instance, for high pressure, there was one experiment conducted at 2,500 PSI and at 52 degrees Celsius. And again, another experiment was conducted at 30 to 90 PSI and 52 degrees Celsius. In terms of duration, we had one experiment at 7 days, and we had another experiment at 28 days that was conducted. So you have my different collaborator in this case. In addition, we also have some other experiment. The goal of this experiment was to understand what is really, how can we isolate the influence of chemistry? Because you have a complex chemistry. If you just look at CO2 saturated brine, it's very complex. But what about trying to look at other fluid that will represent a simpler chemistry? So we started by looking at deionized water, and then we kind of looked at brine. And for the brine, we try to look at the influence of different type of salinity in this case. So the brine tends to be a little bit kind of mildly acidic, but from one type of brine to the other one, you're going to have different ionic strength. And then you have the GI water. GI water would kind of let us know whether you have some type of supercritical reaction that is occurring. So that way you can kind of look at different level of complexity in the environment. You have GI water, you have brine, and then you have CO2 saturated brine. So that gives us one axis where we're trying to look at what is the influence of chemistry. And then you have the other two axes, that is temperature, that is the temperature is in the range of 52 degrees Celsius. And then you have pressure, high pressure, which is 2,500 or 3,200 PSI. Okay. So these are the different environments that we have. So for the microstructural characterization, so very similar to what was pointed before, is a lot of time those experiments are going to be highly dependent on the way the sample is prepared. So literally we spent months just figuring out how do we prepare the sample, because if you don't have the right sample preparation procedure, well, you're going to have erroneous results. So this is our process. We have the host rock, that is Mount Simon sandstone, that was extracted from 2,500 meters underground. Then you're going to embed, and we're going to embed with low viscosity epoxy resin. Then you're going to have coarse grinding. We have different stages of coarse grinding. We have different stages of fine grinding. Then we have coarse polishing, and we have fine polishing. So you can see that what is happening is, as we do our preparation procedure, we are resolving the microstructure. But we have to be very careful, because you want to just kind of expose a fresh surface, but you don't want to damage that surface. So you want to prevent reduce the appearance of scratches or micro cracks or even pitting in this case. So this is what we have, the fine polishing, where everything is very well polished and we don't have like scratches or pitching on the surface of it. Okay. Then in terms of mechanical testing method, we used scratch testing for fracture characterization. So I'm going to show you a video. As MJ said, part of my PhD thesis was to find a way to calculate the fracture property using scratch test. So here's the principle of scratch testing. You're going to have a probe. In this case, you have a spheroconical probe, and you're going to go and kind of push across the surface. And what you're doing, what you're pushing here, let me stop. We are prescribing the vertical force, and we are recording. So we prescribe the vertical force in blue, and we record the horizontal force in red and the penetration depth in black. And then you also have the acoustic emission that is kind of showing peaks. One of the advantages of using that method in this case is really because it requires a small amount of sample. Like the scratch length is a couple of millimeters in this case, and the depth we're going to go is tens of microns to hundreds of microns in this case. And yet we are able to have meaningful information regarding the mechanical properties, in this case, the fracture behavior. What is really good is really like this scratch test enable us to be able to bridge the gap between you have conventional fracture testing method at the micrometer length scale, and then you have molecular dynamic at the nanometer length scale, where it's kind of like challenging to find matching experiment at a lamp scale. Good. So these are some more images. This is kind of a schematic of the experimental setup that we have. And this is a picture, a digital photography image of the probe, after scratch test in this case. So I'm going to go very quickly on the LEFM model that I developed as part of my PhD thesis. But the idea basically is really just to evaluate the stress field array of the probe using the method of complex potentials. And then after that, we apply the J integral to be able to relate the fracture toughness, in this case, to the force and the penetration depth. I'm just going to go quickly over here. One extension of that LEFM model, so we calibrated the model using a model material, in this case paraffin wax, but we also use all the engineering models. So we had ceramics, we had polymers, we had metals, and we even had rocks and cement, just not shown here. So you have cement here, and then we calibrated it. So one way that we actually extended it after my PhD, so I worked on it, was to try to see how can we extend this LEFM model to take into account nonlinear fracture mechanics. So when you have nonlinear fracture behavior with a mix of both ductile and brittle phenomena taking place, and that's actually using, in this case, the energetic size effect law. So for the energetic size effect law, again, the different step is really using dimensional analysis. We use dimensional analysis, and then we start from the LEFM solution. So we have the LEFM solution with the dimensional analysis, where this is going to add a new functional, and the value of this functional is going to be equal to 1 when we are in the ideal cases of a purely brittle processes. So then what we can do is to then use, to do a Taylor expansion around the nominal value, and then based on that Taylor expansion, we're going to have then the energetic size effect law in this case. Again, I'm also going to go there. What was really good is that we were able to also validate that energetic size effect law, in this case on shell, and also organic race shell. Another method that we're using to probe the behavior within the context of CO2 sequestration is going to be nanoindentation. So the principle of nanoindentation is you're going to have a probe, and then you apply the force. Typically, you're going to hold the force constant and unload, and you're going to record the force. You increase the force, then you hold constant and you unload. And during the unloading, you can have this unloading slope that is going to give you the indentation modulus, and the maximum penetration depth is going to give you the indentation hardness. Now we extend this nanoindentation to go to grid indentation. So grid indentation this time is, instead of having just like one large indent, we're going to have a series of small indents. And usually we like to have it in a grid, for instance, 20 by 20. And the idea afterward is really to use machine learning. And in this case, it's just like statistical deconvolution method to be able to identify different chemomechanical phases based on their mechanical signature. So this is a little bit the theory that is behind it, but the idea is at the end to be able to represent this distribution of the indentation modulus or indentation hardness as a weighted sum of Gaussian, where each Gaussian is going to represent a specific chemomechanical phase within the material. Okay, so you kind of have our toolbox here. In this case, we have like SEM, nanoindentation, scratch testing. So let's put all of this together. The first step that we wanted to do is kind of to think about what is the lamp scale. So it's essentially when we think about the behavior of the material, we need to have a conceptual model. And for the conceptual model, we have different lamp scale that we're going to have. We have the macroscopic lamp scale, we have the micro lamp scale, and we have the nano lamp scale in this case. And we want to be able to span close to 10 of the magnitude in this case, from the sub-nanometer lamp scale all the way. In this case, we're going to go, one more second. Yep, I got this one. We're going to go from the nanometer lamp scale all the way to the micrometer lamp scale. And then we're going to couple this, in this case, with homogenization. So if we want to go from nano to micro, we're going to resolve it using grid indentation, but also we have, in this case, micromechanical modeling. And then if you want to go from micro to macro to have an agreement or handshake with triaxial testing, we're going to use linear elastic homogenization. Okay. So let's go then and look at some of the results that we had in the case of the Mount Simon. So we go back again and try to see what is the impact of the preparation protocol, because that's something that we really wanted to see is when we're using this kind of depth-based nanoscale mechanical testing, like scratch testing or indentation, like the result that you have, how is this impacted by the preparation procedure that you're using? And we look here at the fracture behavior. And again, I'm kind of looking at different type of preparation protocol and what's the value of the fracture toughness that is giving on a sample that is not altered. So it's just like Mount Simon sandstone, no alteration whatsoever, but we just prepare with different protocols. And what is the result on the fracture toughness that's measured using scratch testing? But we also link it to the roughness because we want to be able to have a criterion to assess the quality of our protocol. So the criterion is going to be the roughness. So if you look at the 6 method that we have, we started by we just cut it using a diamond saw and we don't embed it. And we have a roughness of 41 micron. Then we can mount an epoxy resin. So we reduce the roughness, but we're still at 10 micron. Then we can try to different protocol, vacuum infiltrated with different type of resin, acrylic resin versus epoxy versus epothin. Epothin is really low viscosity resin. And then we really have the final protocol where it is vacuum infiltrated, and then we have a low speed diamond saw in this case. So again, the speed at which we are cutting it also is going to have an influence on the property. And what we see, what we are showing is actually an optical microscopy picture of the top surface after the preparation process. So you can see that at the beginning, we're really not polishing, we are just creating craters on the surface. And then we have different level of kind of more or less successful polishing, but you still have this issue of pitching and surface scratches. And then the final protocol is where we kind of remove the issue of pitching and scratches. So what you can see is that when you have a good preparation protocol characterized by a very low surface roughness, 0.63 micrometer, this is where you have the highest value of the fracture toughness, 0.88, which would be, and which again agree with result of tabulated values for rocks in the order of 1 megapascal square root of meter in the literature. So it's really important that all the samples are prepared in a very good manner, and that is really a strong quality protocol. Now, this is a little bit also challenging because as we're going to see is when you have this this aging process in CO2 saturated brine, one of the issues that is occurring is just the increase of the roughness of the sample itself. So again, the preparation process is actually very important, and it takes several months to be able to derive it. So then let's look at the fracture behavior once we have that preparation protocol. So we have the different ways where we started with kind of a lower chemistry, GI water, brine 1, brine 2, brine 3, and then we're going to have a complex chemistry, brine saturated with supercritical CO2 at high temperature and high pressure. So again, what we can see is that we start with a very high fracture toughness, and overall we have a decrease. So when we incubate just in the brine at room temperature, we still see kind of a slight decrease, especially this is more pronounced for brine 2, where we have a strong ionic strength. But the highest decrease is when you're going to have incubation in CO2 saturated brine at high temperature and high pressure for 4 weeks. So we really had this first result is that when you're going to have incubation under geologically relevant condition, you have a decrease in the fracture toughness in this case. And we even confirm it by taking into account the nonlinearity in the fracture behavior and using our energetic size effect law to be able to analyze crash tests conducted on both unaltered rock, but also rock that has been incubated in CO2 saturated brine. We still observe this decrease in the fracture toughness. Now we are able to link it to microstructural stages. So this is a SEM picture of the intact rock and SEM images of the rock after alteration. After alteration, we see an increase in porosity and we have the formation of channels. And this is actually linked to mineral dissolution reactions that are occurring. So then we wanted to kind of look at what is happening, what type of mineral dissolution are actually occurring in this case. So we see that there's some type of microstructural damage that linked to a reduction in fracture toughness. But what type of microstructural damage and how can we link them to specific geochemical reactions? So we had to refine our conceptual model for the host rock, where instead of having just a 3-step, we have a 4-step. So we have the host rock, Then we're going to have different mineralogies, siderite, feldspar, quartz, and micropore. And then one of the phase, this type feldspar, is going to be nanoporous itself in this case. And again, to go from one level to another one, we can just apply homogenization method. Good. So we have different type of upscaling relationship that enables us to be able to tie the behavior between one length scale to the other one in this case. And that's kind of an example of what it looks like when you want to go, for instance, from the sub-nanometer level to the nanometer length scale using indentation. What is really good is then we are able to really map the behavior. So if you look at a reference sample that is unaltered, after conducting scratch tests, we are able to identify different mineralogical groups. So we have micropores, we have feldspar, we have quartz, and we have carbonate. And these are the same one that we observe using SCM and SCM EDS, but this time using nano indentation and grid and statistical deconvolution, we are able to visualize them, create a map of the different phases, and we can quantify them. We can quantify the porosity and the fraction of carbonates, quartz, and feldspar, and we can show that we have an agreement to, on the one hand, mercury intrusion porosimetry, but also on the other hand, quantitative analysis using X-ray diffraction. So then the next question that we're asking is, what is happening and how does that microstructure / composition evolve as a result of incubation within CO2 saturated brine? So we looked at 3 conditions. We have the unaltered sample, we have the sample that's going to be incubated in CO2 saturated with brine at 2500 psi and 52 degrees Celsius for 1 week, and then the sample that's going to be incubated in CO2 saturated brine at 30 to 90 psi, so higher pressure, and for 4 weeks. And that's very interesting because if you look at the phase, just like visually, you understand what's happening. So you have the blue phase. The blue phase represents micropore, and the blue phase is just gaining ground. You know, if you look in the second and the third image, you see more blue compared to the first one. And that's actually one thing that we are observing in the sense that we are increasing the porosity. And then if you look at the light yellow, light green phase, that light yellow and light green is receding. The light yellow and light green is linked to feldspar. So we are dissolving feldspar component in this case. So what we are seeing is this increase in micropore and this dissolution in feldspar. But the good thing is using kind of this multi-scale approach that incorporates micromechanical modeling and depth-based nanoscale mechanical testing, we are able to have this connection between geochemical reaction and microstructural and compositional changes in this case. So then we can try to think, what is the influence of geochemical reaction on the elastoplastic properties in this case? We can quantify the fraction of each phases, you know, carbonates, quartz, feldspar, and then the different porosity in terms of microporosity and nanoporosity, and we can tie it to a value of the bulk modulus. So we can just kind of show it what is happening. So for different kind of system, and again, these conditions represent lower, kind of simpler chemistry and then more complex chemistry. And also we have room temperature versus at the end, high temperature and high pressure with CO2 saturated brine. So when we go from unaltered to complex chemistry and in high temperature and high pressure, then we increase the porosity, we decrease the fraction of feldspar, and we decrease the bulk modulus. So because of geochemical reaction, we have microstructural change, we have compositional changes, we have mineral dissolution reaction, and this is going to lead to reduction in the bulk modulus. Okay. What is really interesting is one thing that we tried to do was to use computer vision and to see, using computer vision, are we able to have the same conclusion regarding microstructural and mineralogical alterations? So what we did was, again, to have kind of this large mapping using backscatter electron microscopy. And then we can then quantify, we can then use image analysis and use a different gray level to identify different phases. For the phases, we had then feldspar, we had quartz, and we have micropore and clay, and that's really based on the gray levels. And we can see what happens. So we have on the left, an unaltered sample, and then on the right, we have something that's altered. And we can see we have the same trend is as the result of incubation in CO2 saturated brine, we have increase in the fraction of porosity, we have a reduction in quartz pointing to a dissolution of quartz, but we have the highest reduction in feldspar, we are dissolving feldspar. So it's really good to be able to have, like, on the one hand, you have, like, a nano-indentation, statistical deconvolution, and then on the other hand, you're going to have scanning electron microscopy imaging along with computer vision, and they agree, yes, we are dissolving feldspar, we are increasing the fraction of micropores in this case, and we can quantify it further. One thing that we were kind of looking at is when we look at the mechanical properties that are decreasing, what are the mechanical properties decreasing? So this is why we're really trying to use a different modality for depth-based nanoscale mechanical testing. So we looked at the indentation modulus, the indentation hardness, and we look also at the creep. So log6 creep behavior. So looking at time-dependent behavior, and the result was really the same. Is we have these decreases in the phases, but we also have the decreases in the mechanical properties. So this is shown here. We have a decrease in the bulk modulus, but we also have a decrease in the creep modulus that will occur between unaltered and altered in both cases. So let me summarize what we've learned is that as a result of incubation in CO2 saturated brine, we're going to have an increase in porosity. We're going to have dissolution of feldspar, dissolution of quartz, and we're going to have dissolution of clay. This is what we've learned. And those microstructural and compositional alterations are going to lead to a decrease in mechanical properties. So I'm going to acknowledge my sponsors. So we have CO2, we have the US Department of Energy via the Center for Geologic Storage of CO2 in this case, and then you have also my institution. So on this, I just thank you very much, and I will take your questions.
Sorry, I was muted. Questions for Angie? Maybe to break the ice, I start to ask the questions first. Angie, did your samples have some sort of carbonates in them?
Yes. So we have a lot of feldspar in our samples. Let me go back. Let me show the
first feldspars are these aluminosilicates, potassium aluminosilicates, and sodium aluminosilicates. So carbonates like calcite, other phases.
Oh, we don't for this sample we didn't have calcite. Okay. Let me
very quartz rich, and you know why I got a little bit it was very interesting because I saw that you have some sort of a mildly acidic solution, and then the quartz is dissolving.
Yeah.
So it's kind of counterintuitive because quartz dissolves at relatively higher pH. So this was kind of interesting to me that you observed that even quartz start to dissolve in these conditions. So kind of interesting.
What we think is just like this is the quartz solution. It's not the most favorable thermodynamic reaction, but because of the high pressure also that is occurring.
Very high temperatures, right? But did you have any estimates of what is the pH, in situ or in the experiments that you did in collaborations with others?
Yeah, in situ it tends to be close to 5 because the brine was trying to reproduce. We had 3 different brine with different ionic strength, but we were trying to match the brine that is locally in this case. So I think that for the quartz, it's kind of a result of the high ionic strength and the high pressure that we have. But what is more prevalent is feldspar. Feldspar is really the first thing that we notice. Feldspar is dissolving in this case. And then we have the secondary is going to be quartz. That's okay.
Maybe at that high temperature and high pressure, plus ionic reactions, just quartz reacts with something, forms a secondary phase, and then it dissolves.
Yeah, that was also another
something like this.
That's a great point that you're saying is maybe it could be that we have some type of secondary precipitation that we are not yet able to capture in our system. That's kind of a limitation of my approach because I'm a little bit blind by way of relying on statistical decomposition. It would be good if I could match my indentation with an XRD, superimpose them at the same time. We're still working on that because then you can actually see the phase, not just rely on the mechanical signature. Yeah.
Excellent. Thank you, Angie. Thank you. Chloe, I think Chloe has a question.
Yeah, thank you so much, Angie, for the inspiring talk. As usual, I had a quick question about the orientation of the minerals. Are quartz and feldspar isotropic? Did you notice that they were oriented in general in your materials?
That's a very good question. In this material, they were isotropic. We didn't have any anisotropy. We had a sample experiment that I didn't show where we tried, because typically for anisotropic material like shale, and we've studied shale and organic shale, we take the sample and we look at different orientation and we do scratch tests, and you see a difference. In this case, we didn't have any difference. And even when we looked under the optical microscope, we had the similar picture as what I'm showing of just like the grain together. So for this sample, we didn't see any anisotropy.
Yeah, because I have a similar problem where we're trying to identify biotite minerals, and those are very anisotropic. And my follow-up question was, how would you cluster your data points in such a way that you identify 2 points that are away from each other because they have different stiffnesses, but still identify that this is the same mineral, but just occurring on the surface under a different orientation? And I don't know how we could handle that problem. You can, unless you make the assumption that locally at the scale of the nano indentation test, all the minerals are aligned, and in which case you can identify them. But I don't know how to do that.
One way to do it is actually to just see that the indentation is going to be anisotropic, and that way you have a tensor. So, and instead of, because right now my indentation is only in one direction.
Yeah.
Versus in this case, we would have indentation in at least 2 directions in this case. And that way we have a tensor in 2 directions, and trying then, this time I just expand the space, because currently when I did my statistical deconvolution, let me, sorry, this is not the most easiest way of doing this, but I'm going to get there. When I do my statistical deconvolution, I only have 2 axes. So I have an M and H.
Yep.
I have an M and H. But what I would do then, instead of having just 2 axes, then you can say I'm going to have M1, M2, H1, H2. And then you can better identify those phases by saying that it's just a tensor that I want to be able to characterize. And I just make my space, I increase the dimensionality of my space when I do my clustering. Because currently it's literally, even here, it's just kind of going just to 2 axes instead of making it just kind of more complex and more sophisticated.
That's great. Thank you, Angie. And I had follow-up questions about the homogenization techniques you wanted to use at different scales, but for the sake of time, I'm going to pass on the floor to someone else, and maybe the 2 of us can exchange a few emails about that.
I would love that. All right. Thank you.
We have a question.
Thank you so much.
Pania.
I guess Julian's hand has been up before me.
Okay, so Julian, do you have any question?
Oh, yeah. Hi. Can you hear me? All right.
Yes.
Okay. Thank you, Angie, for the presentation. I like the also what that you mentioned about the sample preparation for SEM and EDX, because I will be having similar struggles in the future, I think. My question is actually, maybe you already answered it when you were answering MJ's question, but were you able to match the nano indentation phase map with the EDX map or with XRD?
So
that will be pretty
what
cool.
we just have a quantitative match or a qualitative match. Let me show you here. What we did is on the unaltered sample, we look at the phase composition and the porosity, and we compared with X-ray diffraction and with MIP, but we are not able to do what I was talking with MJ. Is what I need to be able to do is take my map where I did the where I do the nano indentation and do the SCM medias at the same location. And that way, when I do and then I go back again to my statistical deconvolution, and instead of having just M and H, then I can now add elemental composition from the SCM medias. And that way I would have a much kind of a clearer picture, because right now when I say this is quad, it's kind of based on the value of M and H. But if I had M and H and the silicon fraction or the presence of potassium or no, then I'm kind of, it's more certain. So this is what I'm working on currently.
Okay.
That's a very difficult task, right? Making sure that the 2 maps come exactly on top of each other and match.
Yes.
It's
really
more like an art.
Yeah, I'm collaborating with MIT on that. They are the expert on that there. Yeah.
Excellent. Francois, you had, and sorry, and Pania, after Francois, I'll basically. Thank you. Francois, I think that you had a question.
Yeah, it's also on this kind of graph. It's about the nano indentation data, because As you said, you have different phases. So you have the quartz, the feldspar, and each of them will have a different response. But then the nanodentation could fall on a grain boundary or near a grain boundary. And near a grain boundary, the local stiffness and the local mechanical properties will be very different than in the center of the grain. I was wondering if this kind of effect is discussed in among the people who study nanoindentation, because it means, for example, that when I see these graphs, that is the graph you show here with the points from blue to red, it's possible that one of the green point could be something, a point which would be at a quartz, but very close to a micropore, for example, or a feldspar. And locally, the hardness modulus will be changed by this effect.
Okay, that's a very good point. So to be able to mitigate it, there are two things that we're doing. The first thing is we're working on a grid, so that, you know, just because of the way my SEM, I've been showing my SEM, my sample are not square, the grid are not square, they are very irregular. So that if I have a grid, let me try to kind of show it here. If I have a grid like this, it's unlikely that I will be consistently on the grain boundary. So maybe this is 1 or 2 points, but then very quickly I'll be going away. The other point is we have a very low depth. So the force is 2 millinewton and we are targeting a maximum depth of 400 nanometer again. To make sure that to increase the likelihood that I'm going to be in one grain versus another. So that's kind of one way that I'm going to be doing. Then the other way is when I'm processing my data, let me show it here. Yeah. So what I just said was just to have kind of boundaries, saying, for instance, carbonates, everything that is above 110 gigapascal, that's the carbonate. I'm just not even going to think it. Quartz, usually it tends to be between 80 to 100 gigapascal. So this is where I'm going to put my quartz. And everything else that will be on the level of 60 to 70 gigapascal or up to 70 gigapascal. This is going to be feldspar. And then for the feldspar, this is where I'm going to be using micromechanics to be able to kind of match it. I showed it here. I'm matching it to say my feldspar by definition is going to be nanoporous. So what's the level of my packing density on my feldspar? And that way I have another threshold where I would say, well, at this level, this is going to be microporosity. And I'm not saying that this is perfect, but that's the way that I'm using to make sure that I'm going to reduce the probability of those grain boundaries, and I will target primarily micropore, feldspar, quartz, and carbonates. Yeah.
Okay, thank you.
So I think that, Francois, it all depends on the ground boundary to the, you know, surface ratio. If it's really, really high, for example, then the method will be biased. But if the fraction is small, right, which should be in these cases, then the signal that you get from bulk is far more pronounced than the signal that you get from the interface or grain boundary.
That's a great point, MJ, and it also goes back to the design of my system. Like what we talk about, length scale separation. What's the size of my grid compared to the grain size, compared to the density of the grain boundaries? What's the depth at which I'm going? So I'm trying to have something that is at least big enough to include several grains, tens of grains, 10 to 20 grains in this case. That way, I'm kind of removing this issue of grain boundaries. Yeah.
Making sure that the separations of the scales are properly satisfied. That's great.
Yes.
Pania had a question.
Yeah, thank you so much, Angie, for a wonderful talk. So I have lots of questions. I'll follow up with you, but just one quickly. You mentioned that you were extracting the elastoplastic properties from your mechanical. So I was wondering that which plastic properties did you extract and how did you do that?
Okay, so for the plastic property, we're looking at, let me look here. Oh, we're looking at the cohesion. I'm trying to see where I show it. We're looking at, okay, it's going to be showing here. Good. Okay, so if you look over here, I have the, from the indentation, I have the modulus and the indentation hardness. And by applying backward micromechanics, I can link it to the cohesion of the skeleton here and the friction coefficient in this case. So I can extract it. I kind of assume the friction, because to have the friction, I would have to do indentation with two different probe, with two different angles. So I kind of assume the friction coefficient, but at least I have the cohesion that I have at the lower length scale. And to be able to go upward, what I showed upward, I'm looking just at elasticity, but I have another presentation where we use poromechanics to be able to look at the failure surface. That was actually, I didn't present it here, but we look at the failure surface macroscopically, because if you have the different phases, and for each phase you have the value of C and alpha and M, then you can try to look at the macroscopic level, what is going to be the failure surface of the composite, but I did not present it here.
I see. Yeah. So that's the part that I was interested in. As part of one of those EFRCs, actually, we worked with Mount Simon, and then we look at we use the elastoplastic cap plasticity model to define the yield surface. So I was curious that if there is a relationship when you are doing the homogenization, do we reach out to those models that we use, or those models, are they applicable to your work or not? But thank you so much. Wonderful talk.
You're welcome, Panya. I'm going to be emailing you my paper, because I did that on Mount Simon, actually. So I'm going to email you the paper. That way you have the model that we used.
Yeah, that would be great. Yeah, so because ours was on Mount Simon, and it was part of the EFRC a couple of years ago too.
Nice.
Yeah, thank you.
Excellent. And before closing the session, there is one last question from Jay in the chat box, and maybe
yes.
Angie, you
Let me
can
look at it. Okay.
go through it very briefly. Thank you.
Okay. In geochemical reaction using CO2-induced brine, I was wondering how much the dissolution would be different if you would use only brine and CO2-induced brine to make micropore size bigger, and how would this CO2-induced brine make pore bigger in terms of chemistry and perspective? That's a really good point. If you use CO2 with brine, and that's something I should have clarified, the solution is more acidic, because this time the CO2 dissolves into the brine, because the brine is mildly acidic 5. When you add the CO2, it's more 4, so it's more acidic. So what we've observed is it tends to be harsher. You have higher dissolution, higher increase in porosity, higher increase in nanoporosity. Yeah, that's a great question. Thank you.
Awesome. So with the in the interest of time, we have to, because we are now 10 minutes past the promised 90 minutes. I would like to thank both speakers for their excellent presentation today. And we hope that for the next one, it will be EMI and Georgia Tech, and hopefully we are going to see everybody in person. Thank you, and have a wonderful rest of the day or night.
Thank you.
Thank you
Thank
so
you,
much.
Angie. Thank you,
Thank
Francois.
you. Thank you, MJ. Thank you, Panya. Bye-bye.
Thank you, Bob. Really
Bye.
appreciate it.
Bye-bye. Good
Bye,
weekend.
everyone.